So thank you very much everyone for coming, and thank you to the organisers for inviting me to this What Is talk on causal inference. So Dawid, I'm Richard Emsley from the Centre for Biostatistics in the Institute of Population Health in the medical faculty. And what I'm going to do today is just a very light touch overview of what we mean by causal inference and some of the statistical concepts behind that, but I'm not going to go in depth into any of the methods that you may already be familiar with around causal inference. There's other forums for that. There's resources available on our website that people can freely download, and I'll pinpoint where they are. So firstly, what do we mean by causal inference? Well, this has been debated for a long time within philosophical literature. This is a quote from David Hume from 1739 to 1740, for example, where he's talking about why do we pronounce it necessary that everything whose existence has a beginning should also have a particular cause? And also, why do we conclude that such of these causes must have particular effects further down the line? And the thing that we're going to be focusing on today is the statistical theory behind causal inference. So if you're expecting a philosophical talk around this, then I'm afraid that's not what we're about to hear. But we're going to focus more on the kind of quote which is the second one here by Mervyn Stone, that statisticians must find a sound philosophical basis for causality and be able to express in a precise mathematical form both the knowledge and the assumptions which are needed in order to determine whether something has a causal effect. So throughout there'll be a brief history. That's how we're going to introduce the key topics. So we have here Ronald Fisher and Yossi Neyman, two of the founding fathers of modern statistical science. And in 1923 and 1925, independently, they were discussing in agricultural experiments the potential yield from a plot in terms of crop output. And what Fisher actually did in 1925 was the first introduction of the concept of random allocation within an experimental setting. But this idea was later formalised statistically for both these randomised studies that Fisher had been talking about, but also non-randomised studies by Don Rubin from Harvard. And it uses a concept called potential outcomes, which is something I'm going to spend quite a lot of time explaining. And this was subsequently called the Rubin causal model by Paul Holland. And actually, when I was doing some research for this, the Wikipedia page for the Rubin causal model is actually excellent, really, really good. So that's quite a nice resource. It goes through lots of examples and lots of the key assumptions underpinning this so-called Rubin causal model. This arises from a paper in 1974 that Rubin wrote in the Journal of Educational Psychology, and it was published there because, despite being a well-known statistician, he couldn't get this idea published in the Stats Journal because it was seen as trivial. So this paper, which has really led to the modern statistical ideas of causal inference, now has about 1,000 citations on Web of Science as of yesterday. Rubin was also involved in another key concept in the area, which is called propensity scores, that some of you may have heard of. This is a paper from 1983, which has got nearly 4,000 citations. And I'm not going to talk in depth about propensity scores today, and I'll signpost where there is some resources available from that, from a workshop that we gave last July all about propensity scores. So what's the general principle of causal inference that we're talking about? Well, we often compare a particular outcome after an action has occurred with what would have happened had the action not occurred. So, for example, this morning I had a headache. I took a paracetamol and my headache's gone away. Did my headache go away because I took the paracetamol, or would it have gone away naturally because of the time difference? And so we're often mentally and sometimes unconsciously making these kind of comparisons between what has happened and what would have happened. And if the two outcomes are thought to differ, then we say that this action has had a causal effect. So my headache went away because I took the paracetamol. And the question is, can this be modelled statistically? Of course, the statisticians, what we're told is that statistical models can only tell us about an association between two variables, say X and Y. And the aim here of causal inference is to go beyond this association and say whether we can infer a causal interpretation for this relationship. And there's three main ways it basically does this. The first is by being quite explicit about what the causal estimand is. What is it that we're trying to estimate within the statistical model? Secondly is being explicit about all the assumptions which are being made in order that we can infer causality. And thirdly, and importantly, thinking about other possible explanations for any observed effects that we find, particularly related to the concept of confounding. And causal inference is now a huge topic, both within statistics and outside of it. And so there are many, many methods which purport to give causally valid solutions to the problem. And because of time, I can only give an overview of these. So I'm going to illustrate this potential outcomes framework that we've been introduced, which is also sometimes called the counterfactual approach, and I'll explain the difference. And it's a comparison between what is and what might have been. And so what we want to do is estimate the difference between a patient's observed outcome and the outcome that would have been observed had they received a different treatment or a different exposure. And one of the key things here is that it has to be possible for a person to receive both of these treatments or both of these exposures. And so within this framework, it's very difficult to conceive something like gender as a cause, because at my stage of life, it's impossible for me to become a woman, and therefore I cannot look at the causal effect of male to female. So, it's a comparison. We have an individual, Homer, he receives a particular treatment, and we measure some outcome. Now, if we want to infer that this treatment has had some effect on the outcome, what we want to do is compare what would have happened to the same individual at the same point in time had they received a different exposure, say they received the control. So what we would do is measure the outcome under control, measure the outcome under treatment, and a comparison of these outcomes will give us what we call the individual treatment effect. Now, of course, we can't observe the outcome for the same individual at the same point in time under two different exposures. This is something that's referred to as the fundamental problem. And so what we want to do is find an individual who is as closely matched as possible to the person receiving a treatment and give them the control so that their outcomes may be considered similar. They're not the outcomes necessarily considered similar, but they're considered similar. And so this comparison of the outcomes would give us an estimate of the individual treatment effect. But of course, if we choose the wrong person, then a comparison of these outcomes will not give us an individual treatment effect. So if Homer receives the treatment, Mr. Burns receives the control, then there's so many other factors which can influence their outcome, including age, adiposity, that comparing the outcomes directly will not necessarily give us this individual treatment effect that we're interested in. So what we do is aggregate up to the group level, the average level. So we take a group of people who receive the treatment and a group of people who receive the control. And then we measure the average outcome in the groups. And a comparison of these average outcomes gives us what we call the average treatment effect. And that's generally the parameter that we're focused on estimating. One of the advantages of randomization as a tool, as we'll see, is that it equally distributes characteristics between the treatment group and the control group. So here, for example, we have an equal distribution of gender, we'll see of age, we'll see of adiposity again, ethnicity. And the real strength of randomization is that it will also, on average, equally distribute unmeasured characteristics that we haven't thought of between the two groups. So, nothing within that theory, nothing within this idea that we're comparing the effects within individuals on the two different treatments or two different exposures requires that this treatment effect is equal for everyone. So there can be treatment effect heterogeneity. So here, these four people have a positive individual effect, so there is a benefit to the treatment to these people rather than the control. And for these four people, there is a detrimental individual effect. Therefore, the control would have been the best treatment for these people to receive. But the point is, we're not going to be able to identify this, because all we know is that these people receive the treatment and these people receive the control. I'm going to illustrate this in two other ways. The first, for those of you who are more statistical or mathematically minded, this is some of the theory underpinning this. So if we've got a randomized trial, so we've got two arms, a treatment arm, which I'll call T, and a control arm, which I'll and then some continuous outcome variable that we're interested in measuring. So prior to randomisation, we can envisage that there are two potential outcomes for this individual. There's an outcome we would see if the individual was randomised to receive the treatment, which I'll call as YT, and there's an outcome which we would see if the person received the placebo or the control, which we call YC. So at the outset, there are two potential outcomes that we could observe, depending on which of these two, treatment or control, that the individual gets. And then this individual treatment effect is this comparison between these two outcomes, which we illustrate. And as I say, it's only ever possible to observe one of these, and so the other is this so-called counterfactual. So at the outset, we have the potential to see both outcomes. At the end of the study, when we've collected the outcomes, one of these outcomes will be factual, we will have observed it, the other one would be counterfactual, hence where that different terminology comes in. So illustrating this now with an example, so potential outcomes here, we've just got 9 individuals here. This is the outcome that we would see for each individual if they receive the treatment. This is the outcome we would see for each individual if they receive the control. And then this is an estimate of the individual effect, which here I've just taken as the difference. And this is the point that this individual effect can differ from person to person. There's nothing that says this has to be the same. And these are people for whom, say, the treatment is shown to be detrimental. Excuse me, showing that if a high score is good in some way, but they actually get a higher score under the control than they would under treatment. And this is referred to as the perfect knowledge or God's knowledge, because of course we can't see all these. What we actually get is the observed outcome. So if you receive the treatment, your observed outcome is visible, but we don't know what your outcome would have been under control. And likewise, if you receive the control, we know what your outcome would be under control, but we don't know what your outcome would be under treatment. And so we have no knowledge about these individual treatment effects. And that's why we do this averaging up to compare outcomes across groups. So this is the statistical solution showing the average treatment effect, as I've already alluded to. So we'd say the average treatment effect, or the average causal effect, is the average of these individual treatment effects. And this is the average of all the outcomes under treatment minus the average of all the outcomes under control. Of course, we still can't estimate these. These are still unobserved. But I'm going to show how this can be estimated in some scenarios. So for example, if allocation to treatment is random, so we have a randomised trial, and everyone complies with their allocation, which is going to be a key assumption, then with a bit of maths, you can show that the average of these potential outcomes under treatment when people have received the treatment, minus the average of these potential outcomes when the group have received the control, is equal to this term. And this is observable from within the data. This is the average outcome in the treatment group minus the average outcome in the control group, which can be directly estimated from within the data. So this is the difference in the mean outcome for those receiving the treatment minus the mean outcome for those who receive the control. So even though the estimand that we're interested in is unobservable, we can hypothesize what it is, we can say this is what we're trying to target, and we can estimate it using observational data. This is the underpinning of randomised controlled trials. This is why they're so powerful, because with this simple comparison, they give us an estimate of this average treatment effect. Now, in general, we're still suffering from this fundamental problem, because what we actually observe are conditional effects. That is, if this is the whole population that we're interested in, then some of our group will receive the control, and some will have received the treatment, but no one is in both groups. This is the associational. And this is the different risk observed in two disjoint subsets defined by the actual exposure received. But what causation is trying to get at is what is the different risk in the entire population under both of the possible exposures. So we want to compare what would have happened had everyone received the treatment compared to had everyone received the control. rather than comparing those who did receive the treatment with those who did receive the control. And this fundamentally is why people say association is not causation or correlation is not causation, because they're trying to target different things. But in some scenarios, the two equate, and one of those is randomised trials, as I've illustrated. The problem is that this difference that we can estimate is usually not an unbiased measure of the average causal effect. And there's various maths that I've left out which can derive what it actually estimates. And the key thing is that there are usually some variables, or confounders, which account for the bias in this estimate, in this measure when we try and estimate it, particularly in observational data. And we say that there's no confounding for this average causal effect that we're interested in if both of these conditions hold. And in words, they're basically saying that the mean of the potential outcomes for the control condition is not dependent on whether the person actually receives treatment or not. And similarly, the mean of the potential outcomes for the treatment condition is not influenced by the treatment actually received. And these hold under randomisation, but they don't hold in observational studies, where people choose their own exposure or are exposed to particular things in a non-random way. So the key thing is, why do people receive the treatment or exposure that they receive? The idea of this treatment mechanism, so that we know which of the potential outcomes we actually get to observe. If we have some measurements on variables, then we can say that this assignment mechanism is either ignorable or exchangeable if the conditions on the previous slide hold, so that the potential outcomes are independent of the treatment received given these covariates. And that will always hold under randomisation. And then if we allow for these covariates in an appropriate way, then we actually get unbiased estimates of the treatment effect. And this idea of allowing for covariates, allowing for these confounders which bias our estimates, is the principle of confounding adjustment within observational studies. So, does association equal causation? In general, this doesn't hold. In randomized experiments where the groups are exchangeable, because we assume there's an equal distribution of characteristics between the two groups, so whichever of the groups had received the treatment, we would have observed that group outcome, the mean outcome in that group, because they were randomly allocated. Then under randomization, these associational measures are equal to the causal effect measures that we're interested in, those causal estimates. But if we don't have randomization, then we can't make this claim unless we make some additional assumptions, which we'll come to a little bit later. A note here is that this exchangeability, that we say randomization is really powerful, but it doesn't hold when we have non-compliance or non-adherence to the random allocation, because people are selecting out of treatment because of various factors. So in a perfect randomized control trial, we would recruit patients, we would randomize them to receive either treatment or control. These people would get the treatment, these people would get the control, and then we'd measure their outcome. And we know that by comparing these outcomes, we get an estimate of this average causal effect. The problem is, as everyone quotes, there couldn't be worse experimental animals than human beings. They complain, they go on vacation, they take things they're not supposed to take, they have incredibly complicated lives, and sometimes they don't take the medicine that they've been randomly allocated to. And so what actually happens, instead of our perfect randomized trial, this is a more realistic randomized trial. So some of the people in the treatment group will receive the control, i.e. they won't take the treatment. It's possible that some people in this control group will have access to the treatment, and so they'll receive the treatment. It's possible that people can get something else which is outside of the trial. And all of these things can influence the outcome. And so in this scenario where we're not just comparing the outcome and control, or the outcome under all three of these, we no longer have that property of randomization. We're no longer estimating the thing we think we're estimating. Trials are usually analysed using what's called the intention to treat principle, and this is summarised in the consort statement for reporting of trials as the strategy for analysing data in which all of the participants are included in the group to which they were assigned, regardless of which of the interventions they actually received. So in this case, it wouldn't matter which of these treatments the control group received. They are analysed as though they received the control. And all of these three are analysed as though they received the treatment. And the reason this is so important is because it prevents the bias caused by loss of participants, which disrupts this baseline equivalence, which is so important. And so the idea is that you compare the subjects as they were randomised, just regardless of which of the treatments they actually received. There are problems in only focusing on the ITT effects. So we may, for example, be interested in other questions. So in a screening intervention, we may be interested in the effectiveness of being invited for screening rather than the effect of actually being screened. And they're two different things. The randomisation would be saying, well, what's the effectiveness of being invited to receive screening on your outcome? Whereas this one would be saying, if you are screened, what's the effect of having been screened? It's different from the effect of having been invited for it. These treatment switches will make an ITT analysis conservative in a superiority context. But if you're doing an equivalence trial where you're trying to show that two things are equivalent rather than one being better than the other, it actually makes intention to treat anti-conservative, biased away from the norm. Differences between trials, the so-called effect heterogeneity that we see, for example, in meta-analysis, may be the result of varying levels of compliance, actually rather than heterogeneity in the efficacy of the treatments which are reported to be compared. So ITT results from trials which are put into meta-analysis without any addition of what the compliance rates are in these trials. Then you may find that there is effect heterogeneity between these trials, but that might be because of the varying compliance rather than actual effect heterogeneity, which is what the test is trying to pick up. So what would be a better thing to do if we've got these treatment switches in trials? And this is a key contribution of causal inference to the analysis of trials. So there are a couple of other strategies which are known as per protocol or as treated, people may have heard of, but this is a more valid way of analysing this. So we've got a group of people who are randomised to treatment, some of whom take the treatment, some of whom don't, and we have their outcome. And we call the people who receive the treatment when they've been randomised to it as compliers, and the group who don't take the treatment when they've been randomised to treatment as non-compliers. Now, we have a similar control group, so they've been randomised to control, and within that, there are people who will not take the treatment, and then people also who would not take the treatment. But the key thing is, some of these people would have taken the treatment had they been randomised to treatment, and some of them would not have taken the treatment had they been randomised to treatment. And so we can hypothesize that there's a subgroup here of compliers and a subgroup of non-compliers in exactly the same way as we have in the treatment group. And we know that the proportion of compliers in the two arms will be the same because of randomization. And so what we actually want to estimate is the average causal effect in this subgroup of compliers. That is, the group of people who take the treatment when they've been randomized to receive treatment, and the group of people who would have taken treatment had they been randomized to receive treatment, but they're in the control group. And this is what's known as the Complier average causal effect. So it's the same average causal effect we saw earlier, but in this subgroup of compliers I've just defined. And the reason this is better than the per protocol and the as treated analysis is that it respects the randomization. We're still doing a comparison of outcomes between two randomized groups, albeit smaller groups than the full trial, the full ITT analysis. It's basically the ITT effect in this subgroup of participants who would always comply with their treatment allocation. And so this estimate is not subject to any confounding, and the exchangeability assumption holds as ignorability. And so this is the recommended analysis for trials with non-adherence or non-compliance. It's incredibly simple to do. There's a lot of material on our website about how using a technique called instrumental variables. One of the other success stories within the causal inference literature has come about fairly recently, which is to do with mediation analysis. This is the idea that there is some mechanism or some variable which is on the pathway from exposure to outcome. And we say that there is some kind of direct effect here, but also an indirect effect which acts through this mediator variable. So some of the effect of this exposure on the outcome is acting through this particular variable. Some of it is a direct effect. And we want to decompose the total effect of exposure on outcome into this direct and indirect effect. And this is a quote from David Kenny, who, as we'll see, is a key figure within mediation analysis. He's saying that mediation is a form of causal analysis, causal inference, and that all too often the people who are conducting these mediation analyses don't realize that they're doing it, and so they fail to justify the assumptions which are key in their analysis model. For example, if you only analyze those three variables that you think you're interested in, the effect of exposure, outcome, and mediator, you're basically assuming that there's no other causes of these three variables. Whereas it's entirely possible that there are unmeasured factors, or measured factors, which influence both the exposure and the outcome, or factors which influence both the mediator and the outcome, or factors which influence the exposure and the mediator. So I've drawn these in circles to show that they may be latent variables or unmeasured confounders, or equally they could be measured. And the problem is we can't get any unbiased estimates of, say, the effect of the mediator on outcome when there's this variable here, because this is going to give us a biased estimate of this thing that we're interested in. And if you just follow the standard rules for mediation analysis, it doesn't acknowledge this at all in the well-known Bowen and Kenny paper. This is actually a problem in trials as well. So when we have random allocation here rather than exposure, because it's randomly allocated, we know there's no influences on random allocation in the way that there is on exposure that people select into particular groups. So there can be no arrows going into this random allocation. And so we know there's no unmeasured confounding of this relationship and no unmeasured confounding of this relationship. But what we can't rule out is whether there's unmeasured confounding of this relationship, because we have no control, we can't directly manipulate either the mediator or the outcome. They're just observed as part of the pathway. So there's these potentially unmeasured confounders between mediator and outcome, even in randomized trials. And so even mediation analysis in randomized trials is open to question, unless we consider what are the other possible explanations for this observed relationship that we find. So these could be unmeasured, or if we can measure them, then these are represented here as covariates. They're variables that we can adjust away in the analysis. So this is David Kenny, who's one of the key proponents around the original mediation analysis. He has a very well-cited paper, Bowen and Kenny, from 1986. Dave McKinnon's recently written this monograph around mediation analysis, which makes extensive use of structural equation modeling to estimate these so-called causal effects. And it's absolutely fine to do that, but it is making some key assumptions. For example, we can only get correct estimates of the indirect and direct effects using these procedures if these conditions hold. So that there is a continuous outcome, continuous mediator, so it doesn't work if you have nonlinear or binary outcomes, for example, that all the relevant confounds are included in the models and that there are no additional unmeasured confounds, that's the point I've just been making. We have to assume correct functional form, and that's true within any structural equation model, and also that there's no interactions between treatments and the mediator on outcome. So just to note that bootstrapping is probably the best approach in order to estimate the standard errors of all these, which is in the McKinnon book. And so I said this statistical mediation has three main problems, and then last night I realized there was probably a fourth one as well. Since we listed four, we've not changed that. So there's this unmeasured confounding problem between mediator and outcome. There's this no interactions problem, which could well hold. It doesn't easily extend to nonlinear models. So if you've got a continuous outcome when you're doing regression, linear regression, that's fine. If you want to do, you've got a count outcome when you want to do a Poisson or negative binomial regression. Structural equation modelling isn't well set up to deal with that, although there are ways to do it. We're also assuming that all of these models are correctly specified. And so in the past, maybe 4 years, something called causal mediation analysis has arisen from this causal inference literature which addresses these problems. And this is actually one of the large amounts of methodological research that our Centre for Biostatistics does. So there's a considerable amount of expertise on mediation analysis more broadly, structural equation modelling, but also this causal mediation analysis. I'm just going to illustrate, I'm not going to go through, you'd be pleased to know what all of these are, but the way it does it is by redefining, in terms of these potential outcomes, these counterfactuals, these direct and indirect effects that we might be interested in. And there's various forms of these which target particular questions. And they estimate, for example, the direct effect of random allocation on outcome when the mediator is at a particular level for everyone in the population, not just those who are observed to have it in the population. That's that difference between association and causation that we saw earlier, that everyone in the population has the value. So that's really been a key contribution, because these can be estimated for nonlinear models, for models with interactions, all kinds of different scenarios, and they get over the limitations inherent within that statistical mediation analysis literature. Okay. So this is Jamie Robbins. He's director of the program on causal inference at Harvard School of Public Health. And his main contribution in this area has been to extend this potential outcomes framework that we've talked about to longitudinal settings, that is, repeated measures, and more complex data. And this required a whole new methodology for estimating the parameters, these causal parameters, which he terms the G family. And him and Ruben do not necessarily see eye to eye, and he uses the term counterfactuals, whereas Ruben would use potential outcomes, but they are essentially the same thing. These are current and past members of the Harvard School of Public Health Causal Inference program, and they've primarily been developing estimation methods for within these G family of methods. So you may have, those who are familiar with the area may have heard of G estimation or G forming or G computation. That's where these methods have come from. And this is by far the most widely cited and published group working with causal inference today. So what is their key contribution again? Well, we've introduced the idea of confounding as a problem which limits our exchangeability. So the groups are not comparable because of some factor which may influence them differently. The standard way of dealing with this is to take into account confounders using regression methods, linear regression, logistic regression, just to include these confounders as covariates. But these approaches themselves can be biased when we have time-dependent variables. So we have longitudinal data, we have time-dependent covariates. And if these variables are simultaneously a risk factor for the event of interest, the outcome, but also predicts future exposure, and is itself predicted by past exposure, then we can't use the standard approaches to confounding adjustment. I should say there was a What Is talk on confounding about 3 weeks ago, the slides and audio for which are available, which go through in detail how we can adjust for confounding. So I've deliberately not included anything on that here. But this was the topic, in effect, of Jamie Robbins' first causal inference paper, published in 1986. It's about 123 pages of terse mathematics. And even within that causal inference group at Harvard, I'm yet to find anyone who will admit to having worked through this whole paper. So I wouldn't recommend people go and start with it. But it's an application of a particular thing called the healthy worker survivor effect. And this is the abstract. So it says, in occupational mortality studies, where we're interested in data termination of employment, this is both the determinants of future exposure, because these terminated individuals will no longer receive the exposure, but it's also an independent risk factor for death, if we're interested in mortality, because disabled individuals tend to leave employment in non-disabled individuals. He says, when current risk factor status determines the subsequent exposure and is itself determined by the previous exposure, then these standard methods will not estimate the things we think they're estimating. And this gives rise to the question, which, if any, of these population parameters can be given a causal interpretation in observational mortality studies. So Robbins himself isn't a statistician, he's an MD, doctor in the States, and particularly in occupational medicine. And he was seeing patients in clinic and was trying to answer this particular question, but realised this fundamental problem, that the standard methods which were available in the literature were not going to help. But this effect had actually been observed literally a century before, 1885 by Causal, where he said the more vigorous occupations had relatively lower mortality rate as compared to death rates in occupations of an easier character of the unemployed. This was then termed the healthy worker effect by McMichael in 1974. But Robbins' great contribution in this area was to derive mathematically the concept of the healthy worker survival effect and propose a statistical solution to this time-varying confounding problem, which I'm going to illustrate to you now. So we're saying that these time-varying confounders is a variable which predicts future treatments and outcome, in this case mortality, but is itself predicted by past treatment. And so you can see that this variable is a confounder for this relationship. It influences both of these two things, but is itself predicted by treatments at time 1. And therefore, if we adjust for this variable, which we may be tempted to do, to control for the confounding in this relationship, we're actually blocking some of the effect of treatment on outcome at the earlier time point. And so whether you adjust or don't adjust, you're going to get a biased estimate. So a classic example is treatments called AZT, or HART, which is the drugs which is used to treat AIDS, HIV. So the patient receives AZT at time 1, and whether they receive it or not is based on their CD4 cell count. So their CD4 cell count at time 1 influences their CD4 cell count at time 2. Their treatment at time 1 influences the treatment at time 2. And we're interested in the effect of treatment at time 2 on death. So we know that the CD4 count is a predictor both of death, but also which treatment you're on. Because there are certain thresholds above which the treatment will not be effective. But the CD4 count is directly affected by the treatment itself. And so this is the classic example of one of these time-varying confounders, where the CD4 count both predicts AZT or HART at a treatment time point, but that the treatment also influences these CD4 counts. So this is the example that Robbins talks about. Let's skip that one for time. And basically the problem is this arrow here, that this confounder that we're interested in, this variable that we're interested in, is influenced by previous treatments. At the same time, we're assuming that there's no other unmeasured variables within this system. So there's no unmeasured confounders which influence the variable at time 2 and death, or also influence the treatment at any of the time points. But that's the standard assumption which is made in all observational study analysis, that there's no unmeasured factors out there which could be explaining the relationships that we're interested in by virtue of being related to both of these variables. So in the standard regression models, we would just adjust for these covariates, these variables, as covariates. However, this will fail when the treatment's time varying, because the confounder might be a confounder for later treatment, it should be adjusted for, but it might also be affected by the earlier treatment and so should not be adjusted for under standard statistical theory. So we're in a quandary, we don't really know what to do. So the solution that Robbins proposed, and which is the basis of all these G methods, is to use inverse probability weighting rather than include them as covariates directly in the model. And the effect of this, once you perform the procedure, is to remove all these arrows between the confounders and the treatments, so that we essentially replicate a hypothesis, a randomised controlled trial. So we just see the treatment which is observed at each time point, and there are no arrows going into treatment, because we condition that away as part of the inverse probability weighting. This had never been proposed before. There's been no way to analyse the healthy worker survival effect within studies because the standard methods of confounding control were just not capable of doing it. So this was the original article in 2000, and again, as of yesterday, it had about 700 citations, and it's hugely popular now in the literature in a variety of areas. In the interest of time, I'm going to skip the basic idea. But its key assumption is that we have this confounder, and what we do is we stratify by levels of this confounder to replicate this exchangeability. So within levels of the particular confounder, that this exchangeability, this ignorability idea that we saw earlier, holds. So we basically, within levels of the confounder, replicate a randomised trial. But the problem is that this assumption can't be tested. It's just empirically untestable, that this holds and that there's no other unmeasured factors. So they're widely used in the context, for example, in AIDS research, the classic example, but also now in comparative effectiveness research, where we're interested in the effect of comparing drugs within observational data that haven't necessarily been compared directly in trials, in mediation analysis, to adjust for non-compliance itself in trials. So, for example, if you had randomisation at a baseline and then the treatment at some later time point, well, the randomisation, the treatment you receive could affect the side effects at a later time point, and that will influence whether you stay on treatment or change treatment. But the side effects may also be predictive of outcome here. So there's work around analysing trials using this approach, but also much more common in the literature, the pharmacoepidemiological literature and the mediation analysis, which are already introduced. There are people who really dislike this counterfactual approach, and there are alternative ways of doing causal inference. I'm just going to briefly illustrate two of those. So Judea Pearl developed a whole theory of causal and so-called counterfactual inference based on graphical models and probability theory rather than this counterfactual, this potential outcomes idea. And again, that needed a new method for determining the relationships between these variables, which is the so-called do calculus. This is Pearl's book, published in 2000, Causality, which is very well known, and goes through the step-by-step derivation of this method and graphical models. And the basic idea is that we have these path diagrams, or so-called directed acyclic graphs, where here we've got our observed variables are in boxes, and our latent, our hidden variables are in these circles, these U's. And an arrow between the variables is chosen to represent a true causal effect that we think is there. So there's a true effect of this variable D on this variable 1. And you use the graph to read off conditional independencies. So for example, we know that from graph theory, Y is independent R given these three other variables. So there's lots of theoretical background going into this. But the key thing with them is what's missing from the graph. If these U's weren't measured and weren't on the graph, then we would say, well, there are potentially these unmeasured variables which influence both of these. And so the graph isn't a true representation of what's going on. So if you see a graphical model or a structural equation model which is saying it estimates causal effects, the key question is what's missing from that graph? Are there potentially these unmeasured confounds which could be influencing multiple things? Pearl operates things in terms of this do calculus, this do operator, where he uses the notation do z equals 1 or z equals treatment. And the idea is that you're intervening on particular variables rather than just observing what happens. So it's much more interventional. And it's equivalent to potential outcomes, but it does have this advantage of emphasizing the importance of experimental manipulation, this idea of random allocation. Pearl equates all of his theory to potential outcomes of counterfactuals and shows that they're more or less the same. There is a group who argue completely against using counterfactuals or potential outcomes. For example, Phil Dawid and colleagues, Vanessa and Alo Paswini, who's based in Manchester in our group, they use decision theory or graphical models or stochastic modelling to do causal inference rather than this potential outcomes approach. And they have particular objections, which are that the concepts are deterministic rather than stochastic. So, for example, the potential outcomes for a person are fixed at baseline, and all we're waiting to see is what the assignment mechanism is to see which of those we actually observe and which one we don't. If you think of the example with the table of Rubin's model, we've had all those potential outcomes known, and then the assignment mechanism tells us which of them we'll actually observe in practice. More importantly, we can never learn anything about the joint distribution of the outcome under treatment and the outcome under control because they can't be observed together. And so we can learn nothing about the covariance, the correlation of these. And so even if you could estimate, in principle, these individual effects, you wouldn't be able to estimate their variance, their standard errors. So it's not informative just to have a point estimate without some measure of the variability around that. So they have this alternative approach to causal inference, which if you've disagreed with what I've said about potential outcomes and counterfactuals, may well appeal to you further. Is the terminology important? Well, that's half the debate in the literature, is which should you do it. I quite like this quote that, personally, I see the different formulations as different languages. The French language may be the best for making love, whereas Italian may be more suitable for singing, but both are possible. And in fact, a lot of the argument is, do they boil down to the same thing if you estimate the parameters? And more or less the answer is yes. So whether you use this counterfactual approach, potential outcome approach, or whether you use the decision theoretic approach, what do you actually estimate? In most situations, they coincide. And so the potential outcomes is an easier way to formulate what might be happening and how we formulate causal effects. For those of you who are really interested, there's some recent volumes on causal inference. So this is an update of Pearl's book, which came out in 2009, where he responded to a lot of the criticism of the first edition of the book in print in the second edition. So there's a whole chapter where he takes on the arguments and explains things. So it's quite good, although a bit technically mathematical. This is a new edition edited by Carl Obersweeney and Phil Dawid, but it's actually got contributions from all of the people that I've introduced. And so each person's been invited to add a chapter around causality. It is statistical in nature, but it is fairly accessible as well, and it does have chapters on examples. This is a book about causal analysis for social research. This is a new book which is out in May this year, I think, which I found on Amazon last night. The author's quite well known within sociology, Stephen Morgan. He's written with Chris Winship about causal inference, although on Amazon this book had a price tag of $212 last night, so that one may be a bit prohibitive. These ones aren't so expensive. There's also two forthcoming books on this. So Robbins, who I mentioned, and Hernan, part of his group, are writing a book on causal inference and have been for about 6 years. But the early editions of that are available on their website. So if you look for the program on causal inference at Harvard, you can actually download the first half of their book freely as a PDF. And Rubin, who I also talked about, has got a forthcoming book on causal inference in stats and social sciences. The field has grown so much that it's spawned its own journal now. So as of last year, we have a journal of causal inference, which will publish both theoretical and applied research about causality. And this is, I'm sure this is open access journal, so anyone can get access to papers within there. And they are designed to be theoretical, so it's a lot of the theory, but there are arguments in there about this kind of nomenclature and which is the right way to phrase it. There is considerable expertise for those who are interested in taking any of this further within, well, not just the Centre for Biostatistics, but in Manchester in particular. And this is the Centre for Biostats website. And somewhere buried in the news and events link on the left is a link to workshops. And we give free training workshops. They're advertised within the faculty, but I may well send them to Methods of Manchester as well. Where, for example, we've done a 2-hour workshop on propensity scores. We've done a workshop on this inverse probability weighting, where we go through with examples exactly what's going on. So the previous workshops available to download and all the materials freely available. Thank you for your time.